Hello and welcome to another Applied Flow Technology webinar. My name is Peter Farnham. I am a sales engineer here at Applied Flow Technology, and this is going to be our second installment of the Fast Fundamentals series. This time we're going to be covering AFT Arrow, and in this webinar we'll be covering 10 fundamental modeling tasks, tools, and techniques, and each one of these I'm going to attempt to do in under 3 minutes. So getting into the agenda of what we'll be covering, we'll start off by looking at how to size a compressor in AFT Arrow, move on to using the GSC module. Number 3 will be our global edit feature. We'll move on to sizing a valve or an orifice, then modeling dynamic mixing, sonic choking, using another one of our modules, the XTS module, modeling heat transfer in pipes, sizing a heat exchanger, and then we are going to wrap that up by showing you some of our useful scenario features. So getting into it, number 1, we're going to be looking at how to size a compressor in AFT Arrow. This is the model that we're going to be looking at in just a second. I'll switch to the software. And the purpose of this is going to emulate the first floor of a building. Each one of these pressure junctions right here is going to represent a room in that building, and we're trying to size this compressor right here in order to achieve a minimum flow rate of 250 SCFM of air to each one of these 5 rooms. All right, so getting into the software, this is the model that we're going to be building. I'm not going to build this entire thing in front of you, but for those who are completely new to the software, we have a drag and drop interface. So if I were to build this model, I would start by dragging this tank, this compressor. If I double click on these icons in the left, we call these junctions, it'll keep it active in the workspace. So if I wanted to lay out all of these branches here, then I would be able to build the model like that. And then you just connect them simply by drawing the pipes between each one of these junctions right here. And then once you have this all built, you would double click into each one of these, define the parameters that are required in the system, and go from there. And after that's all defined, you'll go up here, go to the fluid properties menu, define what fluid is going to be moving through your system. In this case, we're going to be using air, and click OK. And once that's all defined and built, you'll see this pilot light in the bottom right corner showing green, saying that we are ready to run the model. So for this example, sizing a compressor, we're going to be looking at the compressor junction right here. There are 3 different modes that you can choose from: compressor curve, compressor map, or sizing mode. Since we're sizing it, we're going to be putting it in the sizing mode. And we're going to make an initial guess of 1250 SCFM flow in order to achieve that minimum 250 SCFM of flow to each one of these rooms. And these pressure junctions are defined as atmospheric, ambient temperature and pressure conditions to represent those rooms in the building. So if we click OK and run this model and go to the output, what I'm actually going to do here is I'm going to drag this output window over to the right so we can look at the model and the output at the same time. So the main points of concern that we're going to be looking at are the outlets of pipe 9, 10, 11, 12, and 13, because those are the flow rates that are going into each one of these rooms. So let's scroll down. We're going to be looking at flow rate. Looks like room 9 is achieving that flow rate. This one's a little low right there, just above that 250 threshold right there, and a little bit low. So it looks like our compressor currently is undersized. What you might want to do now is go back in, and we can do some manual iteration. So let's change this now to 1300 SCFM. Click OK, and let's rerun it and see how we did. 287, 254. This one's still a little bit low, but the other ones look good. So it looks like pipe 11 is going to be our problematic pipe that we need to make sure we size it for, which is logical because this is the farthest away from the compressor. So we will add, say, another 50 SCFM of flow rate, and hopefully that will do it to our system. So now we're at 1350. If we go to our output, think indeed, there we go, 298, 263, 253, 272, and 261. So it looks like we're ever so slightly oversized, but in this case, that could be perfectly fine. And in the next scenario, I'll show you how to use one of our add-on modules in order to achieve that exact flow rate that we're looking for in that most hydraulically remote point. So some of the highlights that I want to touch on before we move on is we just covered how to build a model in the most basic form, define your pipes and junctions, define those fluid properties. For this model, it was air. We showcased the compressor sizing mode, and then we showcased the output. And in that output, I'll get into it in just a second. We can look at inlet and outlet temperatures and pressures of the compressor, which then you can hand off to a manufacturer, and they can provide you with an appropriate compressor curve, compressor map. And after that, you can switch to those different modes that we went over in the compressor and model your system based on truly what is in your physical system. These compressor curves and compressor maps, I'm not going to cover these right now, but we have a couple of other webinars that we have covered in the past. This one, traversing Arrow with compressor maps and how to model compressor head versus flow curves. I recommend checking those out if you want to learn more about Arrow's capabilities in terms of compressor curves and compressor maps. So next, we're going to be building on this compressor sizing model by using our GSC module. This is an add-on to the base AFT Arrow software, and it's useful for getting rid of that manual iteration step that we just went through. So what we're going to be doing, let's go back into the model, switch to that GSC. So the first step to using this GSC module is going to our analysis setup up here in the top. We're going to click on the modules section, and then we're going to activate the GSC module. Make sure it says that it's in use. Now what we can see is the goal seeking control panel at the left is now popping up. So what we can do here is define our variables and our goals in our system in order to achieve that minimum flow rate here at the outlet of pipe 127. So the pipe numbers are a little bit different just because I have a bunch of different scenarios in the model, and those are going to change because you can't have the same pipe number 11 throughout multiple different scenarios. So what we'll do here is we're going to define a variable. We want to vary the compressor, J130. We want to vary the flow in order to achieve a goal of pipe, the outlet of pipe 127. We want to achieve a flow rate of 250 SCFM. So we are varying the compressor flow in order to achieve a flow rate in this pipe right here. Now, this can be stretched to multiple variables and multiple goals. You just have to keep in mind, this is a systems of equations. So if you have three variables, you need three goals and vice versa. But you can add as many as you'd like here. So let's just delete these for now. Hold on, it looks like I might have deleted the one I was going after. Varying flow in the compressor. There we go. All right. Now, click OK. You can see this V right here standing for variable and goal right here standing for goal at the outlet of this pipe. Now let's run this model. You can see the additional section in our solution progress menu, showcasing that we are using the GSC module. Now, if we go to our output, we have these two new tabs up here that we can look at. So let's first go into the goals. Let's see, our goal was 250 SCFM, and it looks like the software was able to calculate a variable that was able to achieve that 250 SCFM flow rate. Now, if we go to the variables tab, it looks like 1330 was going to be the exact value that achieved that flow rate. We can look at that even further in the pipes. You can see 127 has that 250 SCFM flow rate. And also taking it back a little bit to what I was talking about earlier with the compressor inlet and outlet temperatures and pressures, You can look at those here in this junction panel down at the bottom. So inlet, outlet, stagnation temperatures, and stagnation pressures. We also have a compressor and fan summary up here, and these can be helpful for handing off to a manufacturer to give you a properly sized compressor. So some of the highlights we just touched on are those additional analysis setup menus for the variables and goals when you check that GSC box in order to activate the module within the software. And then those additional output tabs that you receive when you are looking and using GSC in the software. We also have a bunch of webinars talking about GSC, and this one actually talks about XTS as well. We'll get into that in just a second. But if you want to learn more about GSC's capabilities, I would recommend going and checking out this webinar. These are all on our YouTube channel. This webinar also is going to be posted to our YouTube channel after it finishes. Number 3. So we're going to be building on the same model for a third time. And in this model, we're going to be using our global edit feature. Let's say you wanted to test a different case where each one of these outlet pipes to each one of the rooms changes from 2 inches to 3 inches. Typically, what you might think is you would have to double click into each one of these pipes and change the variables one by one. But what this global edit feature can do is do that all at once and change everything all together. This extends to pipes and junctions. We'll go over that in just a minute. Let's go to this third scenario. I'm just going to push this output tab right back here. I'm going to move over the model data tab, because what this model data is going to do is showcase what your inputs are to the system in a tabular form. You can look at that by double clicking into the pipe and seeing exactly what it's defined as. You can also right click and hold on the pipe to see this quick pop-up menu. You can see this one's 6 inches. Let's go to this one. You can see 2 inches here. And now let's look in the tabular form. So we're looking at 138 through 142. Let's go to the right. See, all of them are 2 inches right now. We are going to change that using our global edit feature all at once. So if we go up here, there's this little globe icon. If you click that, we have 2 options, global pipe edit and global junction edit. Junction edit will do something similar to the pipe edit, except for all of the junctions. So let's go into the global pipe edit menu. Now I want to showcase some of these selection tools. All would obviously select every single pipe if you wanted to edit everything all at once. None, well, it's going to do none of the pipes. If you had, say, 2 selected and you wanted to invert that, it would invert and select everything else. Now workspace, this is a useful feature, which I'm actually going to go back and show you how I'm going to use the workspace selection feature in this model specifically. And then the select special feature, which allows you to select, say, if you wanted to select all the pipes in your model that have a diameter between a certain value. You could specify that range, select the pipes, and then you wouldn't have to think about it and go into your model, try to figure out which pipes have which diameters, and this select special feature is useful for that. So I'm going to cancel this really quickly. What I'm going to do is highlight all these pipes on the workspace. Now, if I go back into the global pipe edit feature, you can see the workspace pipes are all selected now. So you can do that by clicking this workspace button, invert it, goes to the other ones, back to the workspace. So this is editing all 5 of these all at once. We're going to select our pipe data, where we're going to want to change these from 2 inches to 3 inches. Click OK. Now we're going to apply those changes to all of the pipes right here. We apply those selections, click OK. Now looking at our model data tab, scroll up to the right. There you go. All of them are now 3 inches instead of 2 inches, and that can save you tons of time if you're dealing with models with hundreds of pipes and hundreds of junctions. So some of those highlights we touched on: global pipe edit, global junction edit, doing the same thing that we did with the pipes, except for junctions. Say you wanted to change every pressure in one of these outlet room temperature conditions. And then also the various selection methods. So with the workspace, that select special feature, the all, none, invert, all of those can be helpful and useful when you're building a model in our software. All right, moving on from that model, we are now going to be talking about sizing a valve or an orifice. The methods are very similar, which is why I'm lumping them together. We are going to be building this very simple system over here. A control valve is going to be piped between two tanks. There's going to be a pressure gradient driving the flow between these two tanks. We are now flowing steam. So these are going to be high pressure, high temperature steam going to slightly lower pressure steam. And we want to control the flow in these to 5 pounds per second. And after that, we're going to try to adjust the CV and XT of a valve and the diameter and CD of an orifice in order to achieve that exact same flow rate. So this is how we would go about sizing something like this in our software. Move this back over. All right, so this is our model right here. As I was mentioning earlier, we are now looking at steam instead of air. Click OK. And we're going to be moving a fluid from high pressure, high temperature steam down to a slightly lower pressure and lower temperature steam. Actually, sorry, the same temperature steam, just a lower pressure. That's what's driving the flow. And then in our control valve, I'll very, very briefly touch on our various options. We have pressure reducing. That's going to control the downstream pressure right here. Pressure sustaining is going to control the upstream pressure. Flow controls controlling the flow, and then a constant pressure drop is going to give you a constant pressure drop if you say wanted to estimate a piece of equipment in your system that just as a crude estimation for the purposes of getting rough values, and then you can move forward with something slightly more accurate. So for this example, we're going to be using flow control and controlling the flow to 5 pounds per second. We click OK, run this model, and see what our output looks like. We're going to be focusing on this valve summary here in the top. And the 3 parameters that I want to highlight here are the estimated CV, estimated XT, and the equivalent orifice diameter. So these are not by default turned on. What you're going to have to do is go to our output control window right here, select valves, and then you can see this CV estimated parameter, the XT estimated parameter, and the equivalent orifice diameter. If you add these, this is what's showing in your output, so you can use that for your sizing purposes. Now, using these values, we are going to input a CV and an XT of this into a standard valve and show how that maintains the exact same flow rate, as well as putting in an orifice diameter of 2.345 and showing how that maintains the same flow rate as well. So 99.96, 0.4965, and 2.345. I'm going to pull this to the right so I can reference those values while I am editing this model. So what I'm going to do here is I'm just going to copy and paste. I'm going to copy and paste it one more time. And that way we'll have three different models all within the same scenario. What we're going to do is morph a valve on top of this control valve. So you're going to hold the control key, as you see in that pop-up window, drag the valve over and drop it on top of this control valve, and now it morphed into a standard valve. Same thing goes for an orifice. Hold the control key, drag over, drop, and then it's all morphed there. So going into our valve, I'm going to switch the loss model to CV XT. This was 99.96 and 0.4965 for the XT value. Click OK. Now under our orifice, we're going to do something similar. We're going to change the diameter to that 2.345 inches and use a user specified so we can specify a coefficient of discharge. It's going to be 0.6. For sizing purposes, our software defaults to 0.6, and that's where they are able to get this orifice diameter. So that's why I'm going to be using a 0.6 discharge coefficient. Let's click OK, run the model, look at our output. Well, you can see right here, in every single pipe, the flow is able to be met at 5 pounds per second. The valve summary, you can check and see if there's that CV that we had put in, same as the estimated CV, actually pulls up the same equivalent orifice diameter as well. And that would be what we would call a properly sized valve or an orifice, and you can roll with that in your models. Some of those highlights that I wanted to emphasize, the use of control valves for sizing purposes. So this control valve junction is very useful for doing the sizing calculations that we just did. The additional output parameters, what I'm referring to there is our estimated CV, estimated XT, and our equivalent orifice diameter that allows us to size those different pieces of equipment. And these CV, XT terms can get a little bit more complicated, especially with compressible flow. So there's another webinar here that I'll point you to if you want to learn more about these CV and XT terms we've done. They go into much more detail about what they are, how they're used, how they're calculated, and I recommend you checking that out. All right, the next feature, this is unique to AFT Arrow, is the ability to model dynamic fluid mixing. So in this model over here at the right, each one of these tanks is going to have a different fluid in them, and they're going to combine in each one of these pipes. And our software is able to calculate the mass and mole fraction as they combine into one pipe. So this specifically is supposed to emulate a relief system with 3 different processes, one for methane, one for ethane, and one for propane. And the goal is to determine the mass and mole fraction of the discharge mixture, as well as the relief capacity, meaning the flow rate that all of these different processes combining is going to combine into in this relief system. So let's hop into the model and I'll show you what we're working with. Switch this back over so we can have a bigger workspace. All right. So the first step to dynamic mixing is we want to define the 3 different fluids, or however many fluids you are mixing, in our fluid properties menu. So with AFT standard, which is what we've been using previously, you do not have the ability to do dynamic mixing or define multiple fluids all at once. In order to do that, you need to either switch to ChemPack or NIST RefProp. ChemPack is an additional add-on module that you can purchase separately, but NIST RefProp is built into the software and everyone has access to this. So we're going to be using NIST right now, and you would just search through this list, double click, add to the model, and you can also use this search functionality here because this list is quite long. So we added this methane, ethane, and propane to our model right here. Let's click OK. Now in each one of these tanks, we're going to be defining what fluid they possess. So this first one has methane. You can see the drop-down menu has all 3 different fluids here that we defined. These are high temperature, high pressure processes, hence why we are building a relief system for them. This one has ethane in it, you can see right there. And then this third one has that propane. So let's run this model and I'll show you what we're talking about when we are dealing with this dynamic mixing. So the reason why this model is taking ever so slightly longer to run is because 1, the mixing calculations are a little bit more intensive on the back end, and 2, NIST RefProp uses equations of state to calculate fluid properties as opposed to table lookups in AFT standard. And because of that, the models take a little bit longer to run, but this should be finishing here in just a few seconds, and there we go. So only 30 seconds long as opposed to 1 or 2 seconds, still not too bad. So let's go to the output and look at these various different compositions. We're going to ignore this caution for now. That's talking about sonic choking. We'll talk about that in the next example. So because we defined 3 different fluids, all mixing in one model, we now have this composition tab right here. What this is going to show you based on as a default is it's going to show you the mass flow rates. You can add these composition parameters by going to our output control window right here. And under the pipe, you can see composition mass fraction, composition mole fraction here at the top. You add those to the output, and then you'll be able to look at the compositions in the output window. So let's look at this. So pipe 34 is going to have just one fluid. That's why there's that 100%, 100% for the mole fraction as well. 35 is going to have that 100% of ethane. Same with 36, 100% there. And same with 37 as well too, because it hasn't been combined with 35 just yet. So there's that 100%. Now, once we start getting into pipe 38, you can see those two different percentages, two different mole fractions right there. And then pipe 39, where all of them have combined now, you can see the distribution of methane, ethane, and propane in your system automatically calculated by Arrow. So these are those values. And then also we were talking about relief capacity. The total flow rate of all of these streams being combined together would be 37.627 pounds per second. So some of the highlights that we just touched on are using the NIST RefProp fluid database in order to define multiple fluids and show how they can mix. The different composition tab in the output window, and the additional output parameters to showcase that mass and mole fraction that you have to add through the output control window that we just did. Moving on to number 6. This is another feature that Arrow can do quite well. We also have a lot of other webinars talking about sonic choking, so I recommend going and checking that out on YouTube. As a general overview, we model 3 different types of choking. One is restriction choking. That's what most of you would think of as just standard sonic choking. That's when a flow, say, goes through an orifice or restricted area and it chokes as a result. Expansion choking will happen at an area change, and endpoint choking happens at the endpoint of a pipe, say leading into a tank or the atmosphere. So we have this model over here. It actually showcases all 3 choke points in one model. So let's go to that. I'm going to push this back again. There we go. So for this sonic choking example, we have 3 choke points. I'll showcase how these are shown in our output. One at this area change for expansion choking, one at this restriction for this orifice for restriction choking, and then one at the endpoint right here for this outlet tank. Let's run this, and then I'll show you what the output looks like. So we have this sonic choking tab right here, showcasing that area change sonically choked, the orifice sonically choked, and it choked at the endpoint here at this tank. The warning over here, all this is telling you is that we mathematically cannot calculate the properties in that endpoint tank. What I'm talking about is this tank right here, junction 104. It's just a mathematical limitation. However, all the other properties can be calculated downstream of choke points. That's something that AFT Arrow can do quite well. It's just the endpoint choking is mathematically limited by what we can do. So we highlighted that warning. We have all these sonic choking points that the software was able to calculate. The last thing I want to point out before we get into the graph results and show you how this is graphically displayed is in order to have the software calculate sonic choking, specifically for a restriction, you need to define what's called our CDA for sonic choking. There's a lot of documentation on this on our website as well as other webinars. I'm not going to get into too much detail with what this means, but in order for the software to calculate it, you need to put this parameter in. It's going to be multiplying the discharge coefficient by the restricted area. That's very simple terms, but I recommend looking at our documentation to learn more about that. Now let's go to our graph results, and I'll show you. Looks like, let me run this one more time. We might have lost output. There we go. All right, we're going to select all of our pipes, and we're going to graph the Mach number versus length to show you how this choking works. split the screen, we can look at the model at the same time. So if I click this blue box right here, it'll highlight the junctions where the choke points happen. So J101, that's right here. J103 is right here, and J104 is right here. So you can see this asymptotic approach to Mach 1 showing that choke point, another asymptotic approach to Mach 1 showing the choke point there. And here, it doesn't showcase the Mach 1 approach because the choking itself happens inside the junction. And what we are showcasing on this graph is purely the Mach number versus the length of the pipe. So we're not dealing with junctions. If we were, this would shoot right up to Mach 1 and come right back down and asymptotically approach Mach 1 is at that end point right there. So some of those highlights that we went over, defining that CDA for sonic choking. It's only required for the restriction choking cases, but when you enter that, our software can calculate if your system is choking. The other choke points are automatically calculated with the expansions and endpoints. And then the use of graph results is very helpful for highlighting those choke points and representing or looking at various different things, pressures, temperatures, elevations, all sorts of stuff. All right, moving on to one of our other modules. This is our extended time simulation, or XTS module. What this does is allows you to take a bunch of steady state time snapshots over the course of a transient event. AFT Extreme is our solver to handle any surge effects. So XTS is not going to be dealing with surge. We typically call XTS our long transient solver. So let's say you're trying to charge a tank, like in this example, or close a valve, and all you want to look at is just how the flow is changing, but you don't really care about surges or pressure waves. That's what the XTS module is going to be good for. So for this example, what we're going to be doing is charging this tank right here with 125 psig of pressure. And once it reaches that 125 psig of pressure, we are going to start a transient on our compressor to shut it off over the course of 30 seconds so the tank doesn't become overpressurized. Let's go to that scenario. And here we are. So similar to the GSC module, you'll have to go to the analysis setup, go to our modules, and actually we're going to deactivate GSC for now. We're going to activate XTS. And now this is active in our model. So make sure the transient is marked, the active XTS is marked, and we can click OK. Now what we'll see in this top left corner, or in this top screen, is our simulation duration button. What this is going to do is going to ask you how long do you want to run this transient simulation for. For this case, we want to run it from 0 to 375 seconds, and our time step is just going to be 1 second. So this model is going to give 375 different steady state time snapshots as this tank is being pressurized. We'll click OK. Also, we need to make sure that our tank is being changed from an infinite tank to a finite tank. Has a fixed volume right here that we defined. And then going into each one of these junctions, each one of these will now have different tabs to define transient data. Let's go into the compressor, since that's what we're going to be looking at right now. We have a transient tab, and the first thing I want to point out is this initiation of transient portion. You can initiate the transient event based on 4 different ways. One at just a certain time, one based on a single event, which is what we're doing right now, one where you can cycle between 2 events, and the last one where you can initiate it with 2 events sequentially. For this example, we're doing a single event initiation. So once this tank pressure is greater than or equal to 125 psig, we want to start the transient at its full flow rate, and over the course of 30 seconds, we want that to drop to 0. So we want to turn off this compressor so it doesn't overpressurize. And this additional data point is just to make sure that the transient simulation carries out its full duration. Now there are transient tabs in a bunch of other junctions as well too. Say this heat exchanger, there's a transient in the thermal data tab. You can vary these temperatures over the course of time, and you can vary, say, a valve closure over the course of time by varying the CV, XT. And so for this example, we're just doing the compressor transient, but there are a bunch of other options that you can use with this XTS module. So let's run this. Now we see this transient progress bar. So this is running the model at those 375 different time steps. And we'll look at the output once this finishes in the next few seconds right here. All right. So now I want to showcase there's a bunch of different tabs now up here. So we have compressor transient, valve transient, heat exchanger transient, and even an arrow here to scroll to the right because there's so many tabs. The one tab I want to look at specifically is this event messages by time. What this is going to tell us is at 337 seconds, the compressor transient started. What that means is at 337 seconds, the tank was fully charged to that 125 psig pressure. And we can see that in graphical form. Say if we go to a transient tab, our outlet pipe 73, what you can actually do is right click on one of these and use our quick graph feature. You can see how this pressure increases over a certain range of time. So that 337 right here is right about that 125 pressure of the tank. So this is just a graphical representation of what we can see with this output message. These can also be displayed with our graph results, but quick graph is a quick and easy way to look at that. There's also this progress bar down here too that you can look at how all of these different parameters vary over time by just giving this bar a slide to the right, and then these all change as the transients are happening. So some of the highlights that we just touched on is the transient control and the analysis setup. That's what we defined the simulation to be 375 seconds for. We have the transient tab in several of those junctions. We specifically looked at the compressor transient, but we touched a little bit on how you could do it for a heat exchanger, a valve, a tank, and there are other junctions that can do transients as well. The initiation of the transient, so we initiated this compressor shutdown once the tank reached this 125 psig set point. The transient results in the output with that quick graph and all those additional tabs. And then another webinar, actually this is the one that I was talking about just earlier with GSC, also covers XTS. So if you want to look more into the capabilities, I recommend checking this webinar out. Number 8, we're going to be moving to some heat transfer. So what we're going to be looking at in this system is a machine shop compressed air system. One of these pipes, the entrance to the compressor is going to be assumed fully insulated. However, the rest of these pipes are going to be in ambient 75-degree air, moving at a really slow velocity, 1 mile per hour. But that's going to have an effect on how cool the air is when it exits each one of these tools represented by these exit valves right here. So I'll show you how to define that heat transfer. Actually, before we do so, we need to make sure to turn off the XTS module. We cannot model heat transfer in pipes with XTS just yet. So we'll have to turn that off in order to look at this. So what we're actually going to do is another global edit, because every single one of these pipes, 96 through 103, are all going to have convective heat transfer that's affecting the temperature at the outlet of each one of these valves. So I'm going to drag from the left and highlight all of these pipes, go up to our global edit feature. You see all of those are selected. We're going to select our pipe data. We're going to go to the heat transfer tab. So there are numerous options here. What we're going to be looking at right now is just convective heat transfer, no insulation with an ambient temperature of 75 degrees, and a fluid velocity in the room of 1 mile per hour. There's a bunch of other things that you can define down here as well too, but we're just going to keep these as defaults for the time being. So convective air, 75 degrees, 1 mile per hour, cooling the air in this compressed air system down as it reaches those exit valves. Click OK. Now we're going to apply the heat transfer data that we just defined to those pipes. Click OK. Now if we run the model, we can see what these results will look like. Now, what I would probably recommend is looking at the heat transfer tab. You can see temperatures here, but this is just more consolidated. You can see, let's drag this over again. Let's say we were probably most concerned with the outlets of pipe 100, 101, 102, and 103 because those are the temperatures that are going to be released at those tools in the machine shop. So we want to make sure that they're not burning anyone in the machine shop. So pipes 100 through 103 looks like the fluid outlet temperatures are 196, 188, 177, and 158 degrees Fahrenheit. Probably a little hot. What I might recommend then is this compressor actually was set to an efficiency of 80%. If you were able to bump that efficiency up, maybe get a better compressor for your system, it wouldn't be adding as much heat to the fluid, and the temperature at the outlet of each one of those tools is not going to be as hot, and potentially it won't burn people. So that's how you would model heat transfer inside of a pipe. Some of the highlights is that heat transfer tab in the pipe properties window. That's where we define the convective heat transfer at that 75 degrees Fahrenheit and 1 mile per hour of fluid. And then the temperatures in the results to look at where the temperature of the fluid sits. Number 9, keeping with the heat transfer topic, we're going to be looking at sizing a heat exchanger and some of our options with heat exchangers inside AFT Arrow. So this system at the right here is modeling a natural gas burning system. Each one of these control valves is controlling the flow to the end tanks, which are the natural gas burners. It's keeping them at a constant flow rate. But what we need to make sure of is that the gas is reaching each one of these tanks at a minimum temperature of 100 degrees Fahrenheit in order for the process to work properly. And what we're going to be doing is varying the amount of heat that's going into that heat exchanger at the top in order to achieve that outlet temperature. Yeah. All right, and here's our system. So let's go into the heat exchanger and look at what we have here. Heat exchangers always have a loss model. This one has a resistance curve. We won't touch on that right now since we're concerned mainly with the thermal data. What it's specified to right now is a constant heat rate into this heat exchanger of 500 BTUs per second. What I might recommend to start off with is a controlled downstream temperature. And I'll get into why I would recommend this at first. So let's say in order to achieve an outlet of 100 degrees at each one of these burners down here, we might want to guess that the outlet temperature of this heat exchanger needs to be 150 degrees. So let's click OK and let's run the model and see how we did. So pipe 75, I want to highlight first that in pipe 75, let's go to the heat transfer tab, the outlet temperature or the inlet temperature to pipe 75, outlet of the heat exchanger, was controlled to that 150 degrees Fahrenheit. And what you would want to do, say that was a perfect size, you could go to the heat exchanger summary and see how much heat was actually required to push the fluid to that 150 degrees Fahrenheit. In this case, it was 1,512 BTUs per second. But in this case, I think we're looking at pipes 85 through 89. I think the outlet temperatures are slightly hotter than what we were looking for. So 131, 132, 133. We we're hoping to size a minimum of 100, so theoretically these did meet our specification, but it might be overheating the fluid just a little bit too much. So with that said, we're actually going to jump back into the GSC module and figure out exactly what heat rate needs to go into this heat exchanger in order to achieve an outlet temperature of 100 degrees exactly. Now, because if you look at this distribution, the pipe 85 and 89 are going to be the coolest temperature. We're going to be sizing for one of these based on the heat rate into the heat exchanger. So before we do that, let's switch this back to a constant heat rate in. Let's put 500 for now. And also I'll briefly touch on just the various different options that we have here: counterflow, parallel, enthalpy stagnation rise, various different heat transfer or thermal models for your heat exchanger that you can use to model your specific system. Let's click OK. Now we're going to go to our GSC module. We're going to activate this one more time, and we're going to add a variable now for our heat exchanger. We want to vary the heat rate. Okay, so J83 varying the heat rate in order to achieve a goal in a pipe of a static temperature. Pipe, let's do 85, just the one on the left. So right here, we want an outlet temperature of 100 degrees Fahrenheit. So varying the heat exchanger heat rate to achieve this 100 degree Fahrenheit outlet temperature. These other goals were from earlier, but they're not checked, so we're not going to be applying these to this model. So click OK. Now we run the model and see what we have here. Using GSC and heat transfer is going to take slightly longer, but this model should be complete in the next 5-10 seconds. All right, there we go. So a little bit longer. I guess there might be a lot of things open on my computer as well at this point, so that might be affecting the runtime. But 42 seconds, really not all that bad. That's pretty quick still. So let's look at those GSC variables and GSC goals tabs up here. Let's see, we wanted to achieve that 100 degree outlet of pipe 85. You can see by that G right there and V right here for varying the heat rate. We achieved that goal, and let's see what heat rate we needed for that. Looks like 1,052 BTUs per second. So there you go. That would be a perfectly sized heat exchanger for your minimum case of this natural gas burner system. Some of those highlights that we touched on are the variety of heat exchanger thermal models. We used constant downstream or outlet temperature and constant heat rate into the heat exchanger. We showcase the heat rate outputs, so showing how you're actually figuring out what size heat exchanger you want. This was that 1,052 BTUs per second. And then also using the GSC module, which can be really helpful when sizing a system like this for a remote point temperature that you're trying to achieve. Now, last but not least is our scenarios. So throughout this entire webinar, I've been using scenarios. I haven't touched on them a whole lot. I've been using them for demonstration purposes, but the main purpose of these scenarios is to model different use cases of your systems. So we're going back to our compressor sizing example, and let's say we wanted to test 2 different flow rates of our compressor at 3 different compressor efficiencies. So a total of 6 different models. You can do that all within the same scenario or all within the same model using different scenarios, and you can vary all of those, have propagation happen, and I'll show you what that looks like. So here we are. We are going to be, let's go to the 1250 SCFM. If you remember from earlier, this was our initial guess when we were trying to size a compressor. So let's say we wanted to test 2 different use cases. What I would want to do is, well, I have this base scenario. I could right click, create a child scenario, and that's what I did for each one of these 3 scenarios right here, for an adiabatic compressor, 80% efficient compressor, and 60% efficient compressor. So for these models specifically, I'm going to need to click into each one and adjust the efficiency. That's this box right here. If you don't put anything in, it's going to have 100% efficiency. So we're good there. 80% efficient, put an 80 right there. And then 60% efficient, we're going to put in a 60% right there. Now, if we wanted to test each one of these at a separate flow rate, you don't have to create each one of those scenarios individually. What you're going to want to do is go up to this parent scenario. You're going to right click and you're going to clone with children. Okay, and we're going to do the case that we sized using GSC up there. So that was 1330 SCFM. And there you go. Now we have another 4 scenarios, and these were automatically created. You didn't have to do them one by one. The other cool thing here is if you change this base scenario that is active right now to 1330 SCFM, that is going to propagate down to all of the children's scenarios because they are currently linked right now. So let's just go into the 80% efficient scenario and you will see how that actually worked. So you can see that 1330 SCFM propagated down. We didn't have to define the flow rates or efficiencies for anything except for this one parent scenario. So now we have all of these defined. You could run each one of these individually, but what I like to do is what's called a batch run. So let's go to File, Start a batch run. We're going to add our scenarios, adiabatic, 80% efficient, 60% efficient. Let's just run the bottom 3 for now for example, but you can theoretically do everything in the model. Click OK. Now if we start the run, my hands are off my keyboard, and this is doing it all automatically for me without having to run it one by one. And there we go. There's our batch run status. It looks like we had no errors, so that's great. Let's close this. Now, you might be saying, well, I want to look at each one of these results, but I don't want to have to switch between the scenarios as I'm looking at these results. And to that, I'll say, well, we have a multi-scenario output option for you. So here we go. We're going to our output control here at the top left, multi-scenario tab. Now we're going to select the scenarios we want to view all together. So let's look at all the 3 that we just ran. We click OK. They're going to be colored in a certain way. You can change those with these 3 dots right there. We click OK. Now you can see all 3 scenarios outlined on the exact same output window. You can directly compare these without having to switch back and forth between scenarios. Now, the last thing with scenarios I want to touch on is our comparison tool. So let's say you had 100 different scenarios, and it's really hard to keep track of what did you change between each scenario. That is exactly what our comparison tool is for. So I'm going to this other options menu here, scenario comparison tool. Looks like it opened on my other screen. Here we go. So let's compare just these 3 scenarios that we ran. And these are various options up here to compare certain scenarios. We're doing siblings right now because these are all sibling scenarios. The 1330 is their parent scenario. And then if we click show comparison, and if we mark that we want to only see the differences, we can see that the only difference between those 3 is the nominal efficiency of the compressor. So you see that 80% scenario at 80% adiabatic, which we didn't input, meaning 100% efficiency, and 60% efficient. So those are the only differences within these 3 scenarios. And if you had more differences, these would all show up. And click this to show all, and it'll show everything. No differences. That's why it's being hidden when you select the only differences. So this was our last fundamental. Some of those highlights that I want to hammer home are the ability to clone the scenarios with children, so you don't have to create each one individually. the propagation of those input flow rates or of input parameters in general. We did a flow rate for this, and it propagated all the way down to all of its children. The multi-scenario output, so you can look at the output of multiple scenarios all within one window, and then the scenario comparison tool to make sure that you know what you actually changed between each one of these scenarios. Now, before we go, I want to point out some helpful resources. Docs.aft.com is our documentation and product help site. This will tell you everything from underlying equations to how do you input parameters for a pipe. It gives you an overview of how to use our software, how it works, and it's a great resource for troubleshooting and helping you build your models. Another resource, this webinar actually is going to be uploaded to our YouTube channel in the next week or two. And in that YouTube channel, you can access all of our previously recorded webinars, and I recommend doing so. So those are the ones that I called out previously. You can search for them in our YouTube channel and they should pop right up. This is a great resource for learning technical content, how to use the software, and various other things as well. Now, finally, I want to point out that our phone number, we can contact us at 719-686-1000. If you have a technical or engineering support question, you can contact support@aft.com. And any sales questions that you have, you can contact sales@aft.com. So these are our three main points of contact. We typically try to get back to you within a day or two, and we'd love to hear what you have to say. Now with that, I want to thank everyone for attending. If you have any questions, any remaining questions, please email them to webinars@aft.com, and we will do our very best to answer them. Also, if you have any future webinar topics that you would like to submit, we're always open to suggestions. You can submit those to webinars@aft.com. So with that, thank you all for attending, and have a good day.